All right, so this is a review based on uh, the first exit ticket we did. This is number 101 of our exam review. All right, total mechanical energy is all of the potential and kinetic energy in a system. If you throw a ball up, then as it's going up, it's gaining height, right? And if it's gaining height, that means it's going to have more potential energy. As it falls back down, it's losing height, and so it's losing potential energy. But also, while that same object, you throw it up in the air, it's you're throwing it up, and it's slowing down as it goes up because gravity's pulling in the opposite direction. So it's as it goes up, it's losing potential or kinetic energy. But as it falls back down, gravity is accelerating it, meaning it's speeding up, it's gaining velocity, which means as it falls, kinetic energy increases. So whenever you have objects moving up or down, your one of these potential is being converted into kinetic, or kinetic is being converted into potential. But the total amount of mechanical energy, or ME, stays the same. Okay, that's the law of conservation of energy. All right, this is kind of the same thing. When an object falls, potential energy decreases as the kinetic energy increases, but the total amount of mechanical energy is conserved. Now, in the real world, we have like air resistance and friction and stuff like that. So it doesn't work out exactly the way the math says it should. But that's the difference between working it out in class versus the real world. There are two main types of waves. Compressional or longitudinal is one. That's one type, or a transverse wave. Those, all right. A transverse wave, the matter moves perpendicular to the direction of the wave. All right. So if the wave is moving this direction, I'm sorry, it's hard to draw with my mouse. All right. So if the wave is moving this way, and the molecule is moving up and down and up and down and up and down, that's a transverse wave. All right, so if you were to plot the position of a particle, you would end up with a graph that looks something like this, right? But more symmetrical. And so that's a transverse wave. Okay. Now, a longitudinal or compressional wave, they're the same thing. What happens is the wave is moving this way, okay? But the particles are moving parallel. They're moving back and forth. And so if you think about a slinky, if you took a slinky and you spread it out, you stretched it out, then you would see it kind of like this, right? And that's a stretched out slinky. If you compress the slinky, it might look something like this. All right. So we have a compression, and then we have a stretched out part we're going to call a rarefaction. Now, if I take this compressed slinky and I just stretch out part of it and then I'll let go while holding the opposite end, then what we're going to see is we would see this kind of compressed part bouncing back and forth and back and forth. And so you would see the slinky kind of stretching and compressing and stretching and compressing. So that's what we mean when we say the particles are moving parallel to the direction of the wave. Okay, so transverse waves have crests and troughs. Longitudinal waves have compressions and rarefactions. So again, the part where it's scrunched together, that would be a compression. Where it's stretched out, that would be a rarefaction. Going back to transverse waves for a second. So again, they're going to look something like this. Okay. The line just is supposed to show the original position of the particles. So as the energy flowed through, the particle moved up and then down and then up and then down. And so this up here would be a crest, because the crest is the high point. Down here would be a trough, or the lowest point. Okay. When we talk about charges, like positive and negative charges, two like charges, whether it's two positive or two negatives, they will repel. If we have two opposite charges, they will attract. Opposites attract, likes repel. And the bigger the difference is between the two, the more attraction there would be. Let's see here. Frame of reference is used to determine motion. So if you're riding along in your car and you see the trees going by, you know that the trees aren't moving. They're rooted in the ground. So it must be you that is moving. So the trees are your frame of reference to determine that you are moving. Okay. However, if you're stopped at a stoplight and the car beside you starts moving, you might think that it's you that's moving. It's happened to me. So a car beside me starts rolling backwards or something, and I think I'm rolling forward, and I freak out a little bit. Okay? But also, if something that isn't supposed to move starts moving, then you might get a little nauseated or a little sick. So that when people are riding in a car and they're reading a book, well, every time the car bounces, the book bounces, right? And so, but your brain says, no, books don't bounce. And so your brain thinks that you're not moving because it's staring at a book that's not supposed to move, but yet it feels the movement of the car, and so you get a little car sick. Let's see here. Newton's first law says that an object in motion stays in motion unless acted upon by a net force. So if I had a super slick surface, right, and I've got a little car on my super slick surface with zero friction, and it's moving at say 10 meters per second that way. All right. So once it's moving, I don't have to apply any force to it. If there's no friction to stop it, it will keep moving until a force acts on it. Now, another way of thinking about this, if this car has a constant velocity, then it has zero acceleration. And if F equals ma, if acceleration is zero, then the force applied to make that acceleration must be zero. So, once an object is in motion, it stays in that motion until a force acts on it. If you were up in space and you were doing a spacewalk and your tether broke and you started floating off into space, you're going to keep floating off into space until either you get sucked in by gravity and you burn up in the atmosphere, or you get hit by an asteroid, or hopefully rescued. But yeah, once you're floating in space, you just keep going. All right, this is a heating curve, and so what we're graphing here is energy versus temperature. And so as you add energy, temperature goes up. But the interesting bits to me are that these spots here where energy is going up but temperature is not going up, that's where the melting and freezing occurs. And same thing up here. We call this the boiling point. All right, so this is the melting or freezing point. This is the boiling point or the condensation point. So if we have a liquid and whatever this liquid is, I have no idea what it is, but we heat this liquid up to 80 degrees Celsius, it's going to start to boil, and it's going to keep boiling until all of it has been converted to gas. And then the temperature starts going up again. Okay? Or if we have a gas and we're decreasing the temperature, temperature goes down, energy goes down. And then we get to the boiling point. And at that point, energy is going down and the molecules are attracting each other and getting closer together, but temperature is staying the same until they reach the liquid phase, and then temperature starts going down again until they get to the point where they might start melting or freezing, and then temperature stays the same while energy goes down. The molecules are slowing down and getting locked into place and becoming a solid. All right, so that is a heating curve. The flat areas are changes in state or phase changes. And during a phase change, the energy change has to do with how far apart the molecules are. And then on the slanty bits, the temperature is going up because the energy is causing the molecules to move faster. Remember, temperature is just like the speed of the molecules, kind of. Remember when we're balancing an equation, the coefficients, so like if you have H2H2 plus O2 produces 2H2O. All right? Then this is a coefficient. This is a coefficient. They tell you how many particles there are, how many molecules, or how many atoms. Subscripts tell you how many atoms are in the molecule. So this is H2. That means that in this box, there are 2 hydrogen atoms. In this box, there are 2 oxygen atoms. And in this box, there's 2 hydrogen and 1 oxygen. The coefficient tells me how many boxes I have or how many molecules. So I have 2 boxes of H2. That's a total of 4 hydrogen atoms. I have 1 box because of the invisible coefficient 1. So I have 2 atoms of oxygen total. And on the reactant side, I have 2 boxes of H2O. So I have 4 hydrogen and 2 oxygen total. So this is a balanced equation. Okay? If it's in order to be balanced, you have to have the same number of each atom on each side. All right, and this one we kind of skipped this chapter. The atom of acetine has a mass of 210 and an atomic number of 85. Remember, the top number is the mass. Sorry, I can't write with a mouse. Just hopefully you're following along. So the top number is the mass. The bottom number is the atomic number. It's an isotope of acetine. Which chemical equation displays the alpha decay of acetine 210? All right. So when we look at this, alpha decay ejects a helium nucleus, which is made of 2 protons and 2 neutrons. That means the atomic mass will go down by 4, the atomic number will go down by 2. So if we look here, this atomic number went down by 4. Yay! Atomic number went down by 2. And there's the helium nucleus. So that's a good answer right there. If we look at the other choices, atomic mass went down by 4, but an atomic number went down by 2, but it ejected an electron, not a helium nucleus. So that's not the answer. Here, the mass stayed the same, so that's not the answer. Again, mass stayed the same. That's not the answer. So A has to be the correct answer. All right, so that's the review 101, and I hope this helps you get ready for the exam. Have a good day.